Now, we learned some time ago that kinetic energy is the energy of motion. The expression we used for kinetic energy was 1/2 the mass of the moving object times its velocity squared. Rotational kinetic energy has a similar form. It's 1/2 its moment of inertia times its rotational velocity squared. Almost the same thing. One of the words that we use to describe the old version of kinetic energy we used is we call it the translational, which means moving through space and covering ground. And of course, this would be the rotational. To be able to calculate this energy, you need to know the shape of what's rotating. And of course, you need to know its rotational speed. One of the situations that you're going to come across is when an object rolls along the ground, moving and rotating at the same time. So in this situation, this object has both rotational kinetic energy and translational kinetic energy. The situation that we can deal with is the situation when it rolls without slipping. The reason is because in this situation, when it's rolling without slipping, our relationship between its linear speed and its rotational speed holds. If it's slipping, this does not hold. An example of this might be if you take a bowling ball and throw it down the alley, at first it will slide along and not rotate. That would be purely translational kinetic energy, but eventually it slows down enough where friction can take over and it begins rolling without slipping. At that point, its linear speed and its rotational speed are related by its radius. The total kinetic energy of an object that's doing this is just the sum of the two kinetic energies. But because of the relationship between these two variables, we can simplify this often. Now, this only works if we know the shape we're dealing with and, say, for instance, the linear speed of the object. But what I want to do is let's do a for instance situation where we have, say, a rotating cylinder. The moment of inertia for a rotating cylinder is 1/2 mr squared. What I'm going to do is I'm going to substitute in for here this expression, and I'm going to substitute in for here this expression when it's solved for the rotational speed. What we're going to get then is an expression that looks like this. Now, doing some simplifying, cancel the r squareds, and now you see we've got two expressions that look similar. We can just add those two fractions together and we get this. And this would be this expression that you get for the total kinetic energy of an object that's rolling without slipping if it happened to be a disk or a cylinder. Part is going to change depending on the shape. It will be different if you have a sphere, it'll be different if you have a hoop, or any other kind of, well, those are pretty much the objects that can roll, right? I would like to show you how we can use this to do conservation of energy. So for instance, let's say we have a situation where we have an object that is going to roll down a hill that has a height h. We're going to say it starts from rest. If it rolls without slipping, when it gets to the bottom, it will have gone from having nothing but potential energy to nothing but kinetic energy. But in this case, since the kinetic energy is for an object that is moving through space translationally and rolling, this kinetic energy is going to take on this expression. And again, I do not want you to memorize or make a list of these. I want you to be able to just to derive them from scratch like I did up here, because I guarantee you, if you try to memorize that equation and you apply it to the wrong object, you're going to get bad answers because they won't match. If I know that mgh equals 3/4 mv squared, because we're going from all potential to all kinetic, I can then solve for the speed at the bottom, and what I'm going to get is that the speed is the square root of 4/3 gh. Now, what's significant about this is when we did the same type of problem for an object that moved through space without rolling, just say an object sliding down a frictionless incline, the result that we got every time was 2gh. 4/3 gh is smaller. And it makes sense. If some of that potential energy is being converted to translational kinetic energy and some is being converted to rotational kinetic energy, it will not be moving as fast. The V is being diminished because some of that energy is going into rolling.